All right, so let's go ahead and finish finding these frequencies. So between 200 and 299, let's see, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11. And that was the 42nd piece of data, by the way. Now let's see, 303.99. 1, 2, 3, 4, 5, 6, 6. And then we have 2. So the first question is, add up all those frequencies and tell me what you get. We get 50. How many pieces of data do we have? That's a sign that we did this right. Now, relative frequency is basically the class frequency over the sample size. So for this, basically, we just divide 8 over 50 for 0.16, 23 over 50 for 0.46, 0.22, 0.12, and then 0.04. The total relative frequency should add to 1 or 100%. You could also give that as a percentage if you so desire. Now, cumulative frequency is where it's going to get a little more fun. We find the sum of the frequencies for that class and all previous classes. So for the cumulative frequency for this first group, it's going to be 8. Now, for the next cumulative frequency, we had 8 before that. We added 23 to that, so we would get 31. Now, let's go back to the chart and see how many pieces of data were below 199 or below. Look, 31. So you can see it that way. So the next cumulative frequency, 31 plus 11, that would be 42. Because you had 31 before and then 11 after. And if we go to the 299 mark, or the next one below 300, what would the next cumulative frequency need to be? 48. And then this last one would have to be 50, which should be the original total. And cumulative relative frequency is basically just dividing by 50. All of the cumulative frequencies by 50, because there were 50 pieces of data. That's all, that's why. So we're going to make a histogram of this data using the class bounds and or midpoints. I'm going to do them both. I prefer to use class bounds. And even though the specific instructions are not until later in the calculator, later in this notes, I'm going to show you how this can be done on the graphing calculator. So the highest frequency is what? 23. So so basically the frequency will go on the vertical axis. We can go in fives here. Now, class bounds, I'm going to write those in blue. So negative 0.5 would go here to 99.5, 199.5, 299.5, 399.5, and 499.5. Now, again, I prefer using class bounds, but if you wanted to use the midpoints, you could do that. The first midpoint would be 49.5, then 149.5, 249.5, 349.5, and 449.5. So now, the first frequency was how many? 8. So 6, 7, 8, 7, 8, 9. So I'm going to draw that 8 there. Now, what was the frequency for the next set? 23. We're going to go up pretty high here. Now, I am not going to like pull out a magnifying glass and see that this is perfect or anything. You know, I'm not going to like, you know, do that. Yeah, 23. And the next one would be, and there'll be 11, 6, and 2. Now, I am going to show you how to use the graphing calculator. Now, the calculator instructions are, you know, this was what, page 6. The calculator instructions on how to do it are on page 16 and 17. Now, they're using data, they're using different data here. But this, you know, we have to keep in mind two things: our class width and our X-min. So what we'll do here is, first off, I'm going to go to y equals and make sure all these are clear. Now, we're going to go and do the plot now. So we are going to hit second and stat plot. We're going to choose plot 1. We're going to turn it on, and we are going to choose the histogram. Now, X list is L1 and the frequency is 1. Now, what we need to do is we're now going to go to the window menu. So if you hit window, now what was our lowest class boundary? Our smallest class boundary, what was it? was negative 0.5. What was our largest class boundary? $499.5. Now for X scale, what was our class width? It was 100. Now, the Y min should always be 0. What was our maximum frequency? It was 23. Let's make it 25. Now that you've done that, you hit graph. And if you hit trace, you can actually go between all of this. Now, the nice thing is there's a video on Moodle, a video link on Moodle with this exact information. So you actually don't have to really worry about stressing out here at this point. But that's what you're going to get. Now, so it's pretty cool how it all works. Now, a cumulative relative frequency graph, or ogive, it'll display the cumulative relative frequency of each class of a frequency distribution. So that is going to be a line, like a line graph. So the frequency distribution will be the cumulative frequencies. So let's make an ogive of that previous data. Now this time, the frequencies are going to go from 0 to 50. So we'll go in increments of 10. So negative 0.5, 99.5, 199.5, 299.5, 399.5, and then 499.5. So, how many were below negative 0.5? 0. How many were 99.5 or lower? What was the cumulative frequency? 8. Right about here. So then we'll start connecting. Oh, that's the only thing I don't like about this little pen pad. It's kind of hard. So what about the next one? Well, there were 23 altogether. I mean, there were 23 between this, but what was the cumulative? 31. How about the next frequency, cumulative? $42. So the steepest line is obviously this one. And then it was 48. And then 50. Which line was the least steepest? This last part. That's because it had the shortest frequency. And this is basically how we're going to make an ogive. And again, I am not going to be like picky about how it looks. I mean, it's got to look somewhat reasonable, like you made an effort. All right. Now, let me jump back up there. Now, any other questions about all this before we go on to the other method, so to speak? All right. How can we construct a frequency distribution given the number of classes? Here's the thing. I am going to tell you the number of classes. I'm going to tell you that. You will determine the class width, and it will always round up. Trust me. I've had a lot of students that would say, oh, Mr. Jarrett, I still have one more class to go. And I'll say, did you round up? Because even if you got like 12.05 for the class width, you have to make it 13. Otherwise, it will not work. So, the class width, we're going to do this with 8 classes. So, the max was what? It was 440, and the minimum was 53. And we're going to divide that by 8. So I get a class width of 433. Did I do something wrong here? Did I do something wrong with my calculator? You can tell me yes. You can tell me, if you tell me I'm wrong like that, you will not offend me. Don't be afraid to offend me. I'm not hung up on, I have no ego hang up or anything. What did I do wrong? Oh, I should have put parentheses. 440 minus 53, and then we shall divide by 8, 48.375. Now, we have to round that to 49. Always round up. So, now in this case, our class, it's going to start off with the lowest value, 53. Now, we're basically now going to add 49s until we get to the end. So then we have 102, 151, 200. $347 and $396. Now, it's going to happen to one of you, and I'm not going to like jeer you or insult you when it does, but there's a chance you could have done 48. Now, here's the thing. So this goes from 53 to 101. Now we could just keep adding 49s or go one less. 150, 199, 248, 297, 346, 395, and if I add 49 to that, I'm just too lazy to do it in my head right now. 444. If we had only used 48 as our class width, this would have stopped at 436 or 437, I believe. What's the problem with that? If this had stopped at 437. What's the highest value? 440. Where would that 440 go? That's why. So the class boundaries, we would go from 52.5 to 101.5. Now, I'm not going to make you write out all these class boundaries, but basically, 395.5 to 444.5. The distance between boundaries is how much? How far apart are these two? $49. How far apart are these two? Are they 49 apart? No, these are 48 apart. Remember, class width is from one class to the next. That's where it comes from. And you know what? I don't even like class midpoint. I'll talk about it once, but you know what? Yeah, if you want to do it, do it. I'm not going to. So now we get to figure out the frequencies between these classes here using that same data. So I'm going to give you a moment or two to do that. So for 53 to 101, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 in that first group. Now we are going to have 8 groups here. 102 to 150. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15. So the cumulative frequency was 8 for that first one, and this one was 23. 151 to 199. 1, 2, 3, 4, 5, 6, 7, 8, 8. Cumulative frequency would be at 31. Oh, that would help if I put it in the right place. And again, if I make a mistake, please tell me. Again, I'm not one of those people that hates to be corrected, because I'm not some like super intelligent cyborg that can't, yeah, I'm human. All right, 200 to 248. 1, 2, 3, 4, 5, 5. $249 to $297. 1, 2, 3, 4, 5, 6, 6. And that takes us to 42. 298 to 346. 1, 2, 3, 4, 5, 5. That would take us to 47. 347 to 395. 1. And here's the thing. You could have something with nothing in there. You could have a group with nothing in it. That's okay. Don't freak out about it. And then you would enter the relative frequencies by dividing by 50, 0.16, 0.30, 0.16, 0.10, 0.12, 0.10, 0.02, and 0.04. Then the cumulative relative frequencies, you get those by dividing by 50 or adding the relative frequency beforehand. Either way. All right, not bad at all. So now we get to make our frequency histogram. Now this time we're going to start it at 52.5. So, and the highest frequency was 15. So now since we're starting at 52.5, I'm going to put kind of a lightning bolt here to indicate that. You know, going from 0 to 52.5. And the class width was, what was the class width again? 49. So basically, we would just add increments of 49. Starting at 52.5. Then adding 49ers. 101.5, 150.5. $199.5, 248.5, 297.5, and I might go off the chart here, 346.5, 395.5, and 444.5. Yeah, I went off the chart, so be it. 346. Now, if you want to do this on the calculator, you would also change your X-min to this and your X-max to this. So 5, 10, and 15. So let's see, between 52.5 and 101, let's see, there were 8. and then 15, and then 8, 5, 6, 5, 1, and 2. So that's how you make a histogram. Now, while you're working on that, little FYI. So what has happened is that first session of Collaborate basically has been recorded. That's one of the reasons I did a 10-minute break. So what'll happen is that'll actually go into where Unit 1 is. And if we open this up, and there's no voice. Daggone it. Well, if the voice didn't work for this one, I promise you I will have it working the next time. Because the voice should be working. Voicing. Yeah, see, it's reading that. Who knows? Who knows what the problem is? But yeah, I'll have a link to that. All right, so if we go to the calculator, go to Window and change our X-min to 52.5, our X-max to 444.5, and our scale this time to 49. And if we trace, we had 8, 15, 8, 5, 6, 5, 1, 2. Boom. All right, we're going to make an ogive of this data here using the same boundaries. So yeah, 52.5, and the cumulative frequency, the max is 50. So at 52.5, we would have none. At 101.5, 150.5, 199.5, 248.5, 297.5, 346.5, 395.5, and then lastly 444.5. So at 101.5, what was the cumulative frequency? It was 8. What would the next cumulative frequency be? Not 15, that was the actual frequency. Cumulatively, it would be 23. How about the next one? $31. And then 36. How about after that? $42, probably about here. Then 47, I believe. 48, and then 50. So that's how it all works for histograms. All right, so moving along, we got another one. With 50 pieces of data, we're going to go ahead and figure out some of this. So you'll enter that into your calculator and go from there. And the questions at the bottom of page 12, we're just going to skip that. Yeah. Okay, see, it's picking up my voice here. All right, so you'll enter all 50 of those in your calculator, sort them, we'll figure out the class width, and then go it from there. So I'm just going to put this into L2. All right, so I'm going to sort my list in L2. Now, if you put it in L1, that's fine. So my min is 77. My max is 270. Yeah, 270, yeah, minus 77, and we're going to divide that by 8. And we get 24.125. So what would the class width have to be? 25. 25 is going to be our required class width. So we'd start with 77 here. Our first boundary would be 76.5 because it's 1/2 lower. So then we would just keep adding increments of 25 to figure out our class bounds. So this would be 102, 127, 152, 177, 202, 227, 252. 101. And again, when you see an assignment, I'm not going to make you write all these class boundaries. In fact, on the little block there, it should say not necessary to write them all. So yeah, our maximum value was 270. So yeah, that's why we round up. If we didn't round up, our classes would have ended at 268. It's not good. So then 276.5. And now you figure out all of the frequencies. So 77 to 101. 1, 2, 3. There are 10 of those. Now, the other way, if you feel like being crafty, here's something else you could do. You could actually go to stat plot. This time I'm going to change it to L2. And for the window values, I'd start off at 76.5, and I would end it at 276.5 with a scale of 25. Now, if I were to graph that, see I have 10, 5, and yeah, see, you are allowed to do it this way. 7, 6, 6, 9, 5, and 2. Let's see, that's 15, 22, 28, 34, 43, 48, 50. All right, good stuff. Then you do the cumulative frequencies, and you would go from there. So the relative frequency, we would be dividing each of these by 50. The cumulative frequency, 10, 15, 22, 28, 34, 43, 48, and 50. And cumulative relative frequency. Because here's the thing, I'm going to do this just a little bit differently. And what I mean by that is, how am I going to do this a little bit differently? I'm going to put both the frequency and relative frequency on the same thing. So where did we start that off at? It was 76.5, yes. So 1, 2, 3, 4, a little too much. 1, 2, 3, 4, 5, 6, 7, 8. I think what I'm going to do for next time I have you make one of these plots, I'm going to like put graph paper on or something. Six, 7, 8, 9, 10. Boom. 5. So these are the frequencies. Now, to the left, if I do the relative frequencies, they are basically on the same scale. So yeah, 76.5 to 101.5, 126.5, 151.5, 176.5, 201.5, 226.5. Oh, I know how to fix this. Condense that just a little. That's the magic of 1 minute. So yes, so yeah, 10, 5. It shouldn't be doing that even, but 7669. Five and two. All right, so I do want to just tell you a couple things. So yeah, this first lab assignment, there is actually a copy of it on Moodle. There is a histogram question and a weighted mean question. We should actually be able, come Monday. Wait a second. Yeah. This is listed as due August 27th. Now, I think that might have been that's a Thursday. Okay. Here's the thing. I will accept it virtually or you can hand it in August 27th. So, you can do it then. So, that's how it's all going to work here. So, are there any other questions? All right, everyone, that's going to be it. If you borrowed one of my calculators, please put it back. Have a great rest of your day, and I will see you back here on Monday. So, now the only unfortunate thing about sharing the classroom is I don't have my data entered in the calculator anymore. So, I want to ask a couple of questions. What percentile is represented by a cost of $200? Well, the question is, how many were below the $200 mark? Okay, these were textbooks. How many textbooks were below the $200 mark? Can somebody tell me that? Without having to enter, let's see, was there 200 in here? Well, here's a good thing about making this. Here's 201.5. Now, that does include the $201 textbook, but there were 34 below that, but there was that one that was $201. So, by my calculation, there were 33 of them. So you'd have 33 over 50 times 100%. So that would be the 66th percentile. Now, I'm going to let you see how many were repped by, what percentile is represented by a cost of $125. Well, how many were below that mark? How many? 14. So the 28th percentile. Now remember, percentile it's the relationship. Basically, $125 is the 28th percentile. And since it is the 28th percentile, that means 28% of textbooks are below that mark. So, now we can make an ogive. Now, I'm actually going to take a very slightly shortcut here. Whoops, that is not what I wanted. Copy. So the vertical scale for this here ogive is going to go to 50. since there were 50 textbooks. And I'll tell you, yeah, college textbooks aren't getting cheaper. I mean, they were this bad when I was in school. I mean, 20 years ago for me. Some politicians have tried to, like, I remember when I was living in Virginia, the governor at the time actually introduced a bill that would cap textbook prices at public universities, public colleges and universities in Virginia, but it failed in the state house. It's like, oh man, that would have been good. Yeah, you should see how some of these textbook people live. I mean, yeah, they earned it, but All right, so $76.50, there were none. So remember, ogive is the cumulative frequency. So we would go at 10, 15, 22. Let's see, 22 right about here. And again, I'm not going to like pull out a ruler and microscope and try to read this perfectly, to see. I'm not that insane over this. I don't know, there's worse things to be insane over. 34, 43. In fact, I don't even think I have you making an ogive on your test. I've already written your test. $48 and $50. And then we connect the dots, and you get something like this. All right. Any questions on how we make an ogive? Because again, I'm going to tell you this. I'm not going to require it on your unit test that you make one. You'll be asked to read one, and I'll show you how to do that. All right. So if that's cool, we're going to move forward. And cell phone bills. Now, we're going to do 10 classes. So first thing we got to do, what do we got to do with all of this data? I would put it in your calculator. Close enough. All right, I'm going to type all this in. It'll take just a couple of moments. Hopefully I don't make any typos. Well, I just did. So all I got to do is type over it. How about all that rain this weekend? It was Friday. I play poker. I play online poker with my neighbor. We get into the same sit and go tournaments. And basically what happens is it's a six-player game. 3 remaining players win. So we kind of feed off each other. And how they get by the system, you can't use the same IP address, but fortunately my wireless reaches from my house. So, you would think we would make big bucks doing it, but I mean, we have good times. Yeah, we play on his sun porch, and it was made apparent that his sun porch, the roof needs to be replaced. Yeah, cell phone bills. See, I think in today's world, most cell phones are like as part of bundles. Ours is. All right, so we need to sort this data. So we're going to go to step sorta L1, and it's done. So now our minimum is 47, our maximum is 193. So for the class width, we're going to do 10 classes. And let's see, we get 14.6. So what would we actually want to use for our class width? What's it going to be? 15 is right. So, we start with $47 and we keep adding increments of 15. So 62. When I worked for Radio Shack back in high school and college, and they have like maybe a handful of stores left. They at one time had 7,000 stores, but they turned into cell phone shacks. And you could pay your bill. Now, this was also, we had cell phones in the days before they just became, straight up, you actually had like a limit. And this one guy came in all ballistic because he had a $600 bill. And he was trying to claim we lied to him, which that wasn't the case. I'll tell you, yeah, I worked for Sears on one holiday because the place I was working at had suddenly just shut its doors. And what was it? you can pay your Sears credit card bill. I remember this one elderly woman came in. She was making the minimum payment. I think she had a $30,000 balance. Yeah, but I'll tell you, I mean, she didn't look like she was gonna making any efforts to pay that. But they also had protection that when you went, it was paid off. I mean, I hate to imagine that, but I think that's what it was. That's what I do. Stick them with the bill. All right, so now there are 80 of these. So what we can do is we've got to figure out the frequencies. Let's not worry about the cumulative relative frequencies or the relative frequencies. Let's just not fully worry about that, if that's okay. Because, yeah, this will be our last histogram that we make. All right, so, and if you're like me, one thing I love to do is go ahead and make my histogram on the calculator and get my frequencies that way, or I can count. So let's see. For that first set, 47 to 61, let's see. There were 1, 2, 3, 4, 5, 6. So, and yeah, I'm not going to write them all out, but this is going to end with 196.5. Why do the class boundaries this way? This is going to help us when we do our calculator. Trust me. So 62 to 76. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bills. Yeah, so you just got to figure out all them frequencies. Let's see, 77 to 91. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 of those. Now, how many pieces of data did we actually enter? 80. So one thing I can do, go turn my stat plot on, and I'll choose histogram. My X list is L1. My window values, my X-min and X-max, will be 46.5 to 196.5. And my X scale, I don't want to do that. My X scale is 15. Make the Y-min 0. So far we have something with over. So let's make it 20. Let's see what happens. Boom. So let's see. There were 6, 11, and 13. Then there's 6 again. 7. 13. 6, 7, and 8. And yeah, if you do this on a test or a lab, I mean, yeah, do it this way. That's perfectly all right. And then a 3. So if I do add all this up, oh wait, I can just do the cumulative frequency, 36, 43, 56, 62, 69, 77, 80. Boom. There it is. And we can make the frequency histogram on here. However, I'm really going to sheet a little. I don't draw that good anyway. But yeah, pretty cool. So let's see, $100, what is the percentile? Well, what we have to do is go back into that data and see how many bills were below $100. Oh, I lost count. Come on, go back, go back. Let's see, there were 34 of those below that. Wow, that's a lot. So we just got to do 34 out of 80 and multiply it by that 100%. $42.5, so you could say 42nd or 43rd. I would have accepted each one. All right, $150. Well, we know we're going to be dividing by 80 in each case. But for the $150, how many phone bills were below that? 62. So we could do, 77th or 78th. How about $200? Oh, all of them. 100th percentile. Now, nothing is really ever going to be in the 100th percentile per se in the real world, but in this class where we have a finite amount of data, there has to be the biggest one. All right, we're going to skip the ogive. We're in fact going to skip everything on the next page. So now, here, using the calculator to make a histogram, there's instructions on how to do that. So stem and leaf plots. Stem and leaf plots are actually going to be, the hardest plot that we've done was those histograms. So the stem and leaf plot and other plots are going to be a little easier, I think. So each number is separated into a stem and a leaf. They do contain original values. So for instance, this data here, 2 is the stem and 6 is the leaf. Now, you would be expected to provide a key. 2/6 would mean 26. So how many of you have done stem and leaf plots before? You probably did those in like middle school or whatever. So the following are numbers of text messages sent by cell phone users from a college dorm. Display the data in a stem and leaf plot. So we would use the rightmost digit as the leaf. And so for instance, 78 would be 7/8. So you can do this, you can actually make it unordered first. If your data is just unordered, you can make an unordered plot, then you can make an ordered plot from there. Generally, we're just going to make ordered plots. So we can also make a dot plot where each entry is plotted using a point above, and it's plotted above a horizontal axis, just like you see there. Now, if there's a repeated entry, such as 25, you would have 2 dots. And text messages could be a dot plot as well. So, we're going to make a stem and leaf plot of this data. Now, what we'll do here is, if we want to make it ordered, we probably could just put this into the calculator and order it there. So let's pop all that data into L2 and sort it. Shouldn't take us long. All right, I'm going to bail out of this and sort it. So our minimum is 81 and our max is 221. So like we'd have to put 8, 9, 10 all the way to what? Our stems would start with, 8, because our smallest value for that set of data was 81. And our largest was 221. So we're going to take it all the way down to 22. Now, here's the other thing. Even if there might be no numbers in the 160 range, you never want to skip any stems. So yeah, you never want to actually skip any stems. So we have 1 and 8. 8/1 is 81. Never want to skip stems. So the stems for our 90s would be 1, 2, 5, 5. 7799. And you do repeat them if there are repeats. Any questions so far about this? All right, take a moment and finish that. Stem leaf plot. All right, so in the hundreds, we get 2, 7, and 9. And it's always good to write out the stems, the leaves using similar spacing so that you can easily count if need be. So in the 110 range, let's see. Oh, we just got a 1 and a 2. See, in the 120s, we just have 1, 3, 123. Let's see, 131, we have 1, 2, 3, 8. Let's see, for 140s, we've got, 3 5s and a 7. Let's see, 152, we've got 2 and 3 4s. The 160s, we've got 2 and a 4. Let's see, 2, 4, 5, and 8. Let's see, we've got 3 187s. Let's see, the 90s, 3 5 9. Let's see, in the 200s, we've got 2 1s, 3, and a 7. It's 2 7s. Well, let me see. Maybe I put something wrong down. Well, I do have 50 pieces of data. 1 1 2 3 5. Yeah, I mean, if I make a mistake, I mean, you gotta tell me that, because sometimes I do. I'm not some like freak cyborg or something. You ever have teachers that just hate it when you correct them? Yeah, I'm not one of them. I don't know, there's worse things to deal with. All right, so that, my friends, is how we do stem and leaf plots. Any more questions about these? All right, we'll move on. Yeah, just another example of a dot plot, more stem plot, pie charts. Circle is divided into sectors that represent categories, and the area of each sector is proportional to the frequency of each category. Now, how many degrees would be in a complete circle? 360. Now, some teachers would actually do these with protractors. See, I'm not that insane about it. I mean, if you estimate nicely, yeah. So, the number of earned degrees conferred in 2007 are shown in the table. This is a guided example. If we wanted to use a pie chart to organize the data, so there were 728,000 associate degrees granted in the year 2007. Yeah, you get an associate's here. Bachelors are a 4-year degree. There were 1,525,000, or 1.525 million. Masters typically take anywhere between 1 and 3 years, depending on how you do it. It took me 3 years to do my master's because I only took one class at a time. Your first professional is a little bit, it's beyond a master's, but not quite at the doctoral level. So, like, if I got a doctorate degree, you'd call me Dr. Jarrett, but, you know, I don't have a doctorate degree. You know, but why can't they call us master? You know, Master Jarrett. I don't know. I'll tell you, like, at the last school I taught at in Virginia, we actually had 2 teachers with doctorates. And I'll tell you, if you actually, like, students, one thing, but like colleagues, like if I went up and called, like, oh, hey Sam, and like, it's doctor. So, like, ooh, okay. That, you know, like, I mean, like, if, you know, teachers call each other by a first name, like a faculty lounge. No, they wanted to be called doctor by everyone. So, first thing you do is you find the relative frequency of each. So you have to add that up. Now, an example like this wouldn't happen. Whenever I come up with the examples, it's going to be a nice clean number, and the relative frequency will be a nice terminating decimal for each of these. And then what you do is you take each relative frequency and multiply it by 360 degrees to get the corresponding central angle, and just round to the nearest degree. Now, there might be a case where this doesn't add exactly to 360. It might add to 359 or 361. That's okay. Now, if your angle's added to 370 something, you did something wrong. But again, the relative frequencies are always going to be nice terminating decimals on my examples. So you draw the chart here. Yeah, you can see that 1/2 of the degrees conferred in 2007 were bachelor degrees. You have masters and doctorates. All right, we're going to make a pie chart of this. Car brands registered to Wayne Community College students. So the first thing you've got to do is add up all these. We're going to do, the relative frequency for each, and then the central angle. So the first thing you got to do is add up all of these and get the true count. $2,500. See, when you divide each of these by 2,500, you are going to get a very nice, reasonably nice decimal. So for this, 413 out of 2,500 for Hondas. You get 0.1652. And I'm not going to show this calculation each time. Then we're going to take that whole thing and multiply it by 360. 59 degrees. So then you do the same thing with Toyotas and GM, Chrysler, Fiat. Fiat, fix it again, Tony. Ford, fix it, repair, deal. I just like to make jokes. It's funny though. My dad calls Nissans, he'll either call it Nissan or Datsun. Volkswagen. Anyone know what Volkswagen is German for? People's car. Now, the original way I actually had this problem written was most like car thefts by Green. And Toyota cars are the most stolen. Why do you think that is? Well, not being car thieves, you probably shouldn't know that, but basically they take them for the parts. 512 out of 2,500, that would be 0.2048. So the central angle, we'll multiply that by 360, and that'll be 74 degrees. So the Toyotas are going to have a larger piece of the pie. So GM, (1168), that's going to be 42 degrees. Chrysler, Fiat, they're pretty low. Well, one time Jeep was owned by Chrysler. I don't know who owns Jeep anymore. You get 0.1432. Or, Ford, found on road dead. 0.1724. And Volkswagen, 0.1252. When I was buying my first brand new car, and my only new car, I still have it. I bought 13 years ago, I bought my PT Cruiser. It was either that or the Volkswagen Rabbit. And I'll tell you, like, Volkswagen Rabbit looks to be a small car, but I could fit very nicely, had a lot of headroom in there. So basically, we find the central angles for Nissan, that'll be 52, then 62 degrees for Fords, and then 45 degrees for VWs. Now we're going to make a pie chart label. Now, let me tell you something. On your test or lab assignment, this is 90% of the pie chart problem. Figuring out all that. That's 90% of it done. The other 10% is drawing the pie chart. And if you want to be fancy, you can. I'm not. Do that. So we'll start here. And let's see, 59, 60 degrees, probably something like this. Honda, so 74 degrees from there. And this is probably going to be pretty ugly. You know what, close enough. GM, definitely a smaller piece of the pie. And Chrysler Fiat, even smaller. Nissan are a larger piece of the pie, maybe a little larger than that. And then you have Ford and Volkswagen. Yeah, I mean, you can use protractors. You all know how to use a protractor, I assume, if you want. I'm not going to like put this under a microscope and like, oh, we put 60 degrees for the Honda. I better take points off. No, I ain't got time for that. Although COVID has freed up my schedule from things. Basically, yeah. All right. Pair 2 chart, basically. Oh, I'm sorry. I'm so sorry. Any other questions about pie charts? Yes, no, good. All right, well, we'll come back if we need to. All right, one of the other types of charts that I'm going to talk about are pair 2 charts. They're a vertical bar graph where basically the height represents frequency and they're decreasing. I'm going to put pair 2 charts on the test. I just want to kind of make you aware of them. So in a recent year, the retail industry lost $37 billion in inventory shrinkage through breakage, pilferage, shoplifting, and so on. So if we used a pair chart to organize this data, employee theft is the largest cause of inventory shrinkage. Now, I find that to be rather hokey. Why? Here's the thing. Employee theft, as somebody who's worked in retail, employee theft is much easily reportable than shoplifting. And I'll tell you, I worked with some real dingbats. So paired data sets. Now, this is just a very brief introduction to them. We're actually not going to be dealing with paired data until, especially scatter plots, until the tail end of the course. Data are graphed in a scatter plot. They're plotted in a coordinate plane. So this British statistician introduced a famous data set called Fisher's iris data set. It describes various physical characteristics such as petal length and width for 3 species of iris. The petal lengths from the first data and the petal length from the second data. Now, as it turns out, there seems to be a relationship between length and width. You know, now that doesn't, now, and I'm going to say this again at the end of the course, that's not going to mean that, you know, it's a causation. So another set of data could be waist circumference and arm circumference. You know, and it goes to show, all right, we think there is a relationship between one's waist circumference and their arm circumference. Now, yeah, I mean, I'll tell you, when I was younger, yeah, I've always had a gut, but I'll tell you, my arms were scrawny. I would have probably been somewhere like in here, called an outline. Time series is basically another scatter plot, but instead with data over time. You know, cellular subscribers and the average bill in dollars. And it goes to show that the average number, number of subscribers has been increasing rapidly since 1998. You know, I worked for Radio Shack around this time, and one of the things that they wanted us to do was sell everybody a cell phone. And like, you know, it would actually say like, oh, are you interested in a new cell phone today? You know, personally, I don't like being badgered by a store clerk, but, you know, the market we thought was pretty well flooded here. But, you know, people do get multiple phones, you know, for their jobs or whatnot. So, all right, so now we're going to get into measures of central tendency, some of the more fun stuff, the mean, median, and mode. The mean is basically the average amount of data, average of data. Now, this funny-looking symbol before the X represents the sum of a set of values. Basically, whenever you see this, this is a sigma. That means you would add the data ordinarily. Sigma notation. I don't know if they covered that in, I know in Virginia it would be Algebra 2, so you would have probably seen that in Math 3. I don't know. X is the variable used to represent individual data values. There could be subscripts as well. Now, little n represents the number of data values in a sample. Big N represents the number of data values in a population. Now, but it's all calculated the same way, trust me. Now, differentiating between little n and big N is important, particularly when we get into confidence intervals and hypothesis testing. But for now, you know, we're just going to leave it, you know, be. So the mean of a sample is represented by X bar, and it's calculated by dividing the total sum of data over the number of observations. Now, all this is just fancy schmancy jargon. Now, you're also going to learn a bit of the Greek alphabet in here. So, the mean of a population is represented by what looks to be U, but it's pronounced mu. Now, we're going to see that mu a lot more, particularly when we get into confidence intervals and hypothesis testing. And that sample mean is going to be an estimator of the population mean. So, means, sample means drawn from the same population, they take every data value into account, and they tend to vary less than other measures of center. Disadvantages are that they are sensitive to every data value, and it's not a resistant measure of center. So one extreme value could throw that off. Like, I'll give you an example. At the school system my wife and I worked at in Virginia, they are one of the lower paying school systems in Virginia. Well, you know, the cost of living was also low. So, you know, it worked out. But they like to claim that the average salary was a lot higher than it was because they had some teachers that were making, you know, they had a lot of older teachers making more money. So to find the mean, let's find the sum of this. So you just got to figure out the sum of that data. So the grand total of all of this is $3,695. So the mean, we would take that $3,695 and divide it by what? 7. Now, round it to the nearest penny, so the mean price is going to be, bless you, $527.86. Now, hopefully by the end of today, we'll actually be able to figure out all of the ever important measures of center, such as mean. Now, another one is median. Median is the middle value. So if we wanted to find the median of those flight prices, we would order that, and basically, I always like to do this, you know, cross them out until we reach the middle. Median is middle. But what if there were an even number of entries? Well, we would have 2 in the middle. Basically, you would just have to take the average or the mean of those 2. Now, that's also going to take us into quartiles in a few minutes. But we're going to let the calculator do the heavy lifting for us in that case. So, the median price of the flights is $427. I'll tell you, when my wife and I flew from Raleigh to Vegas, 2 round-trip tickets was $340 on Southwest. Now, other airlines started at, well, no, Frontier wasn't as bad, but see, Frontier Airlines, they nickel and dime you on everything. You know, like if you want to, like Frontier would have been roughly the same price if we didn't have any luggage or any carry-ons. You know, and it's like, well, what the hell is that? You know. All right, so the median of these flight prices is $427. Now, if I took the $432 one out, we would want to reorder that data. And if you notice, there are 2 in the middle. So basically, you'd have to find the mean of those 2. And that would be $412. Now, the mode is the one that occurs the most. Mode, most. Now, if no entry is repeated, the data would have no mode. Now, there could be multiple modes. You know, in that case, we would have maybe a bimodal or a multimodal situation. So if I wanted to find the mode of this set, does anything repeat? Yep. Mode is $397. Now, here's the thing. Your calculator will not calculate the mode. You have to find that out for yourself. So another guided example, in a political debate, a sample of audience members were asked to name a political party, and the one that occurs with the greatest frequency in this case would be Republican, because it had the largest frequency. So the mean, median, and mode all describe the typical entry of a data set. The mean is a reliable measure because it does take into account every entry. However, the mean is greatly affected by outliers. Here's another situation. In where my parents live, they now claim that the mean property value is like this much because they built a couple of $1-million homes in a neighborhood. I mean, my parents aren't in a $1 million home. I mean, judging by what people are paying up there, I mean, yeah, it's 200,000, but they have 5 acres, so they bought those. Long story short, my dad bought that land so that someone else wouldn't and build a construction company there. But it's all theirs. But yeah, data can be artificially flawed by outliers, or what we would call in college maybe a curve breaker. You know, if everyone does so poorly on a test, you know, let's say like the mean could have been like a 20, but you know, you're looking at a lot of you and your friends and you all got like 10s and whatnot. Somebody got 100. You know, that's what, you know, the mean can be influenced by that very easily. So here's what we're going to do. We're going to find the mean, median, and mode of this. So we're going to enter this data into the calculator. You can do it into list 1 or whichever. It doesn't matter. But we're going to enter that into a list. And I'm going to show you how to do it with the calculator. Much easier. There are 20 pieces of data. Ages of students in a class. So I'll give you another moment to get that data entered. All right, so now there are instructions on how to do this in your calculator to do the 1var stats. They are on page 49. They start at page 49. However, I am going to show you how to do it here. So that data that we have, we're going to do a 1var stat on it. So I'm going to quit out of this, and I'm going to do a stat. And this time, instead of going to edit, I'm going to go to calc. And I'm going to choose one var stat. And by default, the list will be L1. If you put the data into a different list, just change it. Leave the frequency list alone. We go to calculate. Boom. Now, in fact, what I am going to do is I'm actually going to copy. I'm going to have to scroll down and sort of recopy. And you'll see why in just a couple of minutes. So one var stats so one var stats, pay attention to some of the ones here. This is the mean. This second one, sigma x, that is the sum. It actually adds that up for you. And this would be the sum of the data squared. Now, these are standard deviations. We're not going to worry about that just now. And there are 20 pieces of data. Now, the median was 21.5. And, Q1 and Q3 quartiles, we're going to figure those out probably by the end of class. But, so the mean was 23.75. The median was 21.5. What was the mode? What occurred the most? 20. So, why are the mean and median so relatively different from each other? Because of that outlier, that 65-year-old. This is actually data from a class I taught one summer. Yeah, most of the students were in their 20s, but there was one old guy. And that always seemed to be the case. Always like one older person. I always like to look at my class data. Almost every class I've taught here, there's always been someone like my age or older, but that's not the case here. So yeah, that's how we do it. And there's also instructions on the video how to access the one var stat. Doesn't that beat the crap out of having to do all that by hand? Yeah, because here's the thing, folks. In the real world, if you have large amounts of data, you're going to be using technology to analyze it, not by hand. You're going to be using technology. And that's all there is to it. Now, you could reorder this data, so we're going to put the mean, median, and mode. We're going to figure that out. So the mean, median, and mode. So we're going to enter that data and see what happens. These were 40 randomly chosen people in line at the 2016 election. Do you have to reorder? No. So now we need to figure out the mode. Now, one thing we can do, let's sort that data that's in L1. And let's see if we have any repeats. Well, so far we have a repeat of 35. So 35 occurs twice. Oh, we do have 37 occurring 3 times. So far we have a mode of 37. Let's see if we have anything else occurring 3 times. So we do get 2 modes out of this. $37 and $68. Our mean was 50 and our median was 49.5. Now, could 80 have been an outlier? Well, we're actually going to have criteria to determine that. Or could 19 have been an outlier? Well, again, we'll have criteria to determine outliers. Probably hit that in the next class. So again, how to do 1-bar stats. There's also, if you go to Moodle, short video and calculator basics, you can also figure out how to do, your 1-bar stats there. All right, any questions on this? All right, we're now going to involve a weighted mean. Now, finding a weighted mean, it's the mean of a data set whose entries have varying weights. So basically, we add the sum of the individual times its weight and then divide by the total weight. Now, when it comes to grades, the total weight for that would be 1 or 100%. So your grade is determined from 5 sources: 50% from your test mean, sounds familiar, 15% from your midterm, 20% for your final, 10% for computer lab work, and 5% from your homework. These are the grades respectively. So what happens is you multiply each score by the corresponding weight. Now, let me give you a little hint. One thing I might say is I might give you some percentages, and the rest is this. What would the percentage always have to add up to? 100. So let's say you have 93% of the grade written down. The remaining 7% would be that. I always like to throw that in there just for fun. So you multiply each score by the weight. And then you're going to add those weights together. And since this is dealing with a grade, you just take 88.6 over 1, and you would get 88.6. No, you did not get an A in the class. Close, but no A. It happens. Finding the mean of group data, basically you can approximate it by finding midpoints. I'm going to tell you this, there's none of that on, you're not going to be doing any of this on my lab or anything. Because this is just approximation. So what happens here is for each class, you found the midpoint and the frequency, multiply the midpoint and the frequency, add all that together, and divide by the frequency. So the mean for this is 41.8 minutes. How many mean number of minutes you have spent online during your first or your most recent session? So again, I'm not a fan of this because this is more of an approximation. For this amount of data, they can just give you the raw data. But I did throw that in there, for book. So let's say your grade in physics is determined by 15% lab work. So for the lab, that's 15%. Homework would be 15%. Quizzes, 20%. Midterm, 20%. And 30% for the final. Now, first thing is first. Do all these add to 100? All those percentages add up to 100? Yeah, they do. So let's say you got 87 on the labs, 98 on the homework. Let's see, how did you do on the quizzes? 81, 68 on the midterm, 93 on the final. So you figure out the weighted components. So 0.15 times 87, and let's not round. $13.05 points. I want you to take a minute and see if you can figure that out. So for the homeworks, now see the problems I give, I like to make the weights all different just to mess with you a bit. It's fun. Oh no, it's so we do the calculations. So 0.15 times 98, that would be 14.7. 20 times 0.81 would be, or 0.20 times 81, 16.2, 13.6, and 27.9. Now see, when I was an undergrad student at the University of Pittsburgh, or Pitt, now see, when I say Pitt here, people think, oh, Pitt Community College. We had the one letter grade rule for the final exam, even though like it would be weighed, like your final grade in the course could not be more than one letter grade higher than what you got on the final. So like if you got a D on the final, you couldn't get higher than a C in the course, but mathematically it worked out anyway. But I had a student with like a 99 going into the final. She's like, what if I get a low grade on the final? She could have gotten a 68 on the final and still had an A, but I said, if you got a 98 going into the final, you're not going to get a low grade. And she didn't. Well, also finals for common courses like college algebra and like calculus were common departmental finals. Like unless you were in a night section, everyone took the same departmental final. So the final grade is an 85.45. And we would just divide that by 1. So there's your final course grade, 85.45%. That's pretty good. What do you think hurt you? That midterm is what hurt you. Because, yeah, see, like these weights, 20%, you lost 6 points from the midterm. I mean, you could have made an A. I mean, but still, getting a D on the midterm and then a B in the class, that's pretty darn good. Now, our grading scales here are much easier because we don't do plus-minus grades. Can somebody tell me, does ECU, like, or NC State, do they do plus-minus grades? I don't know. There's been the case for plus-minus grades for and against it. Now, in my case, against it is someone like my dad seeing an A- and say, well, you didn't really get an A. And at which point I would say, well, I would like to see you do better. Could you have done better? No. Well then, but yeah, I think there is a bit of an argument. Someone like an 88% should weigh heavier than should be better than 81. Yeah, when I was a TA. I worked for an instructor that if you got an 80, like that was actually a B. He didn't do B- for low Bs. Now, I mean, if you got the B+, you got the B+. Yeah, that would probably be a good policy if we ever went to plus-minus. Now, what happens is you would get grade points. This is how your grade average would be calculated. Certain classes have certain amounts of credits. How many credits is this class? 4. This is 4 credits. Now, what some people have come up to me in the past and say, Mr. Jarrett, I got an A in stats and a C in this class and a C in this other class, but my average was over a 3.0 because this was a heavier weighted course that had a larger impact on your grade point average or quality point average. So here's how you would do a weighted mean like this. Well, first, your class, calculus. Your credits, there were 4 credits. And your grade, you got an A-, that would be 3.75. You could make a separate column. But points, 4 times 3.75, where did the 4 come from? That is the number of credits. And the 3.75 is what came from the grade. Now, at Wayne Community College, this would have been an A, this would have just been a 4. And yeah, that's the case that people would have against plus-minus grading, but 15. So for stats, physics, chem, and chem lab. I know, like at Pitt, our chemistry courses, the lab was a complete separate grade. So in stats, you get an A, you get a C plus in physics, C minus in chemistry, and a D in the lab. So you're going to have to calculate all of your points. So for stats, 4 times 4, 4 credit A, that's always good. 4 times 2 1/4, that's a 9. 3 times 1.75, I believe that would be 5 1/4. Yep, 5 1/4. And 1 credit and 1 point. So what you have to do now is add up the total points that you earn. Now, what would happen is, your transcript would actually have like the total number of points you've earned over your time. So if we add all this up, 15, 16, 9, 5 1/4, and 1, that is 46 1/4. Now, that is not the answer we're looking for, because what do you think we're going to have to divide to get the GPA? By what? Not 5, but, okay, yeah, and that's, now, we could have divided it by 5 if all 5 of these courses weighed equally. How many credits did we take? 16 credits. So, in rounding it to 3 places, that would be a 2.891 for the semester. So 2.891 for the semester, while during, yeah, you had a D in that chem lab, that hits you a bit. But kind of sucks, your hard work in statistics and calculus. But yeah, this is how it works. You would always be dividing it by the number of credits. So yeah, so overall, so when I read my undergrad transcript, I earned 120 some credits. I had so many points, that point total would be divided by the number of credits, and there's my overall grade point average. Now, I will tell you this, your employers, when you get that degree, they don't necessarily want to see your diploma, they want to see your transcript. Yeah, becoming a math teacher with a C minus in organic chemistry, that doesn't really cause for concern. But what if I were going to be a chemistry teacher? That might be a cause for concern. Overall, I'd like to say, my grades improved my last 2 years in college, and where they say a lot of people do worse in their last 2 years because they're 21 and they're partying more. Yeah. But some of the things I did was, even though I didn't go any further in chemistry, I actually repeated this lab following semester with a much better instructor, and I turned that into a B+. So what happened was, this grade, it still shows up on my transcript as a D, but it's not counted. And that's the way it would work here. Like, if you repeat a course, it's not calculated again. here. And now see, one thing I wish colleges would do, now, like I could have argued, why can't you just remove this from my tree, as if it never happened, because whether or not I took this chem lab, that wouldn't have made a difference in whether I graduate or not. I don't know. I mean, I'm happy with what I got. I got a good job. So we could find the weighted mean here. And I'll give you a minute to figure that out. Yes, calculating your grade average here would be much simpler because we don't do plus minus grades. So to figure out the weighted mean here, all you would have to do is take that 7,201 and divide it by 78. And you get 92.32. Not bad. All right, any questions about finding weighted means? All right, so I just want to tell you this. A problem like where I give you percentages and something like this is going to appear on your tests. If you look at these lab assignments, if you haven't done so, pick this up on your way out. Problems from the labs are really where I love to get my test questions from. Hint, hint. That's where I love them. All right, so I know we're running short here and we're in a good shape. Symmetric distribution is where a vertical line can be drawn through the middle of the graph, and the resulting halves are approximately here. Notice that they are not exactly. They could never be exactly. The data is like exactly symmetric. That could be a case where maybe it was manipulated or something. Who knows? But the mean, median, and mode are the same thing. What if the data are not symmetric? They could be skewed or uniform. So skewed, if it's not symmetric and extends one side to the other. If it's skewed right, got a longer right tail. If it's left, has a left tail. So basically, just look for a symmetry or skewness. So this data on the left has a longer tail. So this is what we would call skewed left. Yeah, think of like roller coaster. Like this is skewed right. I love roller coasters. That's an example of skewed right because it has one a longer tail than the other. And uniform is where the frequencies are equal or approximately equal. And while it is technically symmetric, it doesn't have a peak. For symmetric, it would have to have a peak. So I give you about 2 minutes and see if you can figure out these on the next page. And word to the wise, you will see a problem like that on your test. Another cell. All right, so for this first one, what are we thinking? That one looks to be skewed right. How about the second one? This is skewed left. How about this green one? Symmetric. And how about the red one? Uniform. And there's a question on a lab assignment about this, and you'll definitely encounter one like this on your test. Hint, hint. Now, we go to the next page, even though we haven't discussed box and whiskers, same rules apply. This would be symmetric. How about for the second one? Skewed right, longer right tail. So how about this last one? Skewed left. All right, everybody, that's going to do us for today. So if you haven't picked up a copy, all right, so this is section 2.4. Yeah, the objectives for this section are how to find the range of a data set, how to find variance and standard deviation of a population and of a sample. We're not going to worry about empirical rule. I'm just going to gloss a little bit over Chebyshev's theorem and how to do standard deviation and coefficient of variation. Shut the door, please. Thank you, ma'am. The range is going to be the difference between the max and the min, and the data has to be quantitative. Oh, yeah, this is what I wanted to point out here. So when you go to the Moodle page, under assignments, yeah, what you'll see is all these assignments. Under Unit 1 test, I've put in study prep. So what I've put in here is a couple of old test keys. So when you look at that, these are the types of questions that I'm going to be asking you. Word to the wise, study them. By the way, when you do take your test, this is another key, another review. So, yeah, like this problem here, this deals with the empirical rule. I've actually moved that to Unit 3. So, you know, we're not going to cover this here yet, but we will cover it at a later time. So, yeah, you can see all that good stuff on Moodle that can help you with this course. All right, so with that in mind, so a corporation is going to hire 10 graduates. The starting salaries for each graduate are shown in thousands of dollars. So, whoopsie-doo. So, these are their starting salaries in thousands of dollars. We want to find the range. Now, we can order the data, whether it is with, you know, whether we do it by hand or by the graphing calculator. we see that the minimum is 37 and the maximum is 47. So the range is 10. Now, keep in mind this is $10,000. Range of starting salaries is 10 or $10,000. Now, yeah, how would you feel if you were starting out and someone that just graduated and started with you is making $10,000 a year more? I wouldn't like that. So for this data, the range of ages in a class. What do you think the range of this set is going to be? Well, we will have an outlier, yes. But we're still going to keep that in mind. We're still going to figure out the range. The range is going to be 65 minus 20 for 45. 45-year range. Yeah, like I'll give you, another, I don't want to say weird, but my father, he was 7th out of 8 kids. In fact, my uncle, his younger brother, my grandparents had 8 kids over, bless you, 22 years. So, yeah. But they had 4 within 6 years, and then they had 4. Yeah, it was like grouped in a way. So what we want to do now is the deviation. Now, we're going to talk about standard deviation and variance. Now, first, we got to figure out what exactly is deviation. Well, deviation is how far the difference between a particular data entry and the mean of the data set. Now, whether or not we're dealing with population or sample, it is still calculated the same. So we're going to what we're going to do here is we're going to figure out all of these deviations. Now, first thing we need to do is figure out the mean. Now, you could have figured out the mean, by plugging all this into list 1 and then using the graphing calculator. Now, you could have done it that way. Either way, the mean is going to be 41.5 thousand. Now, when I give you a problem like this, the mean is always going to be a whole number. Whether it's on a problem set or a test, the mean is always going to be a whole number because I don't like dealing with decimals with this. So what we want to do now is calculate each deviation. So from each of these, we calculate the deviation, that x minus the mean. And some of these are negative, and some of these are positive. So what that means for us, some of these are negative, some of these are positive. What is going to happen is all of these deviations will add up to 0. Now, that's not really how we're going to calculate standard deviation. Well, what we have to do is figure out variance and then standard deviation. So the population variance, basically what we're going to do is we're going to end up squaring each and every one of these differences. Because when you square a negative, what does it give you? It'll give you a positive as well. So the sum of squared deviations is always going to be positive. And that's what this is. So that's the sum of squared deviations, and then we ultimately divide that by n, the number of pieces of data. And to find the standard deviation, well, that's even simpler. All we have to do there is take the square root. Take the square root, and we're done. That's for population. Now, I am also going to show you how to do all this on the graphing calculator. So here is everything like in words and symbols. So what we're going to do is now find the population variance of this data. So scrolling on down to page 40, we square all of these. All this data, all of those deviations are squared, and we add that up. And so the sum of squared differences is in fact 88.5. So the population variance, we take that 88.5 and divide it by 10. The reason it's divided by 10 is because what? There are 10 entries. And the population standard deviation, we take the square root of 8.85. Let's get a better approximation. 2.97. But this is in thousands of dollars. So the population standard deviation of this data is approximately, $3,000. Or 2,900, basically, for all intents and purposes, $3,000. The purpose of standard deviation is to measure spread, how far the data are spread. So, with that in mind, first thing you need to do is find the mean. So I'm going to give you, first thing we need to do is find the mean. Whether it's a sample mean or population mean, they're going to be the same thing for purposes of our calculation. So we now have our mean. So we want to calculate each individual deviation. So 73 minus 50, which is going to be 23. Now, I'm not going to require that you show the calculations here. What I am going to require is, you tell me what the deviations are. But basically, to find each deviation, what do we subtract from each of these? 50. Now, 23 squared is 529. So, you have 68 minus 50, which is 18. 18 squared, it's going to be 324. Now, 33 minus 50, that will be negative 17. Now, when we square negative, we get a positive out of it. Negative 17 squared is going to be 289. So what I want you to do is find the remaining deviations and the squared deviations. So yeah, I'm not gonna, like this would be 7, 2, 3, negative 24. That's a big one. Negative 3, negative 11, 21, 9, negative 13, 20, negative 29, 7, and then negative 13. So then we square all of those. So 7 squared, that's 49. Then we'll have 4, 9, 576. 121, 441, 81, 169, 400, 841, 49, and then 169. Now, thing is, if you add up all the deviations, you are going to get 0. In a way, that's checking our work when we add up those deviations. Now, if we add up those square deviations, we're going to get a 4-digit number. Well, it's not always going to be a 4-digit number. But if you got a 3-digit number, it's not enough. If you got 5-digit, it's too much. So when you add all those up, what's it going to be? 4,060. Very good. So now we're going to be able to find the variance. So for the variance, we're just going to take the 4,060 and divide it by what? 16. Why is it 16 this time and not 10 like the previous example? 16 pieces of data. That's right. So if I do 4,060 divided by 16, this is going to be 253.75. Now the standard deviation is the easy part. All we have to do there is take the square root of that variance. So the square root of 253.75, we can round that, and I will tell you clearly how many places I want. Let's just do it to 3 places. 253.75. We get 15 point, well, we'll call it 15.93. So there is our variance and our standard deviation. Now, we're going to do plenty of examples of this, so it's not like, I'm just going to say, good luck, have fun, So, all right, so, now, in addition to population variance and population standard deviation, folks, we'll have sample variance and sample standard deviation. Now you're probably thinking, what the heck are we doing this for? Now, what this does, it is going to be larger than the population counterparts. What happens is it will differentiate between those and sample characteristics and give us a more conservative estimate. Now, basically, here's what happens. We're going to see this much more in Unit 4 and 5, why the whole sample calculation came about. But the variance and standard deviation are very similar. You still find the sum of squares. Now, here's the thing. Even though for population this had a mu, it is still the same old sum of squares that it was before. Now, see, what a lot of students might do is, when they make their formula sheet, they might just read through the notes and put up any formulas that they see. But basically, this means sum of squares, the same exact sum of squares that we calculated before. But instead of dividing by the sample size or population size, it is one less. Now, what that actually has to do, it's called degrees of freedom. But that's above our pay grade right now. So instead of, like, if there were 16 pieces of data, instead of dividing by 16, we would be dividing by 15. That's all. We take the square root the same exact way. You take the square root of the variance. Now, they do have the sample variance labeled as S squared as opposed to sigma. This is lowercase sigma for population. Now, we're also going to see it this way on the graphing calculator in a little bit. So, a guided example here for those 10 hired people, if we wanted to calculate the sample variance and sample standard deviation, here, the sum of squares. Did the sum of squares change? No. So since the sum of squares did not change, yeah, it's calculated exactly the same way. But the variance, instead of dividing by 10, we'll divide by 9. And then take the square root. Now, we're going to work through an example here. So using those 16 ages that we had before, we're going to find the sample variance and the sample standard deviation. So what was the sum of squares? Randomly chosen people and their ages. The sum of squares was 4,060. So the sample variance, we take 4,060, but instead of dividing by 16, what are we going to divide by now? 15. And let's round that to 3 decimal places. $270.667. and we take the square root of the variance. We get 16.452. Now, I'm going to rewrite, so these are the sample characteristics. The population, the variance, and the standard deviation. The variance was 253.75. And the standard deviation was 15.93. If you notice, the sample statistics are larger. And I'm going to give this explanation again. But I like to share this explanation anyway. Basically, it covers more room. It gives us more room for error when we do sample statistics. Long story short, the Guinness Brewery found that using population statistics, they were measuring the content, like they were measuring content, flavor content and such with their beer, and what they were doing was throwing away perfectly good beer. With sample statistics, that gives you a little more room for error, a little more conservative estimate. And that's all we really need to do at this point. So, for this data below, I'm going to ask you to find the mean, sample variance, sample standard deviation, population variance, population standard deviation. And we'll round everything to 3 places. All right, so again, some of these deviations are going to be positive, some are going to be negative. 32 minus 50, that's negative 18. Negative 18 squared. That is going to be 324. Let's see, we get negative 19, negative 5, negative 4, negative 1, 1, 3, 7, 11, and 25. $121 and $625. So we need to figure out the ever important sum of squared deviations. What's that going to be? 1,532. That is correct. 1,532. Now, my friends, that's going to be able to give us all of our necessary statistics. So, population variance, we get 1,532, and what do we divide it by? 10. Well, that's going to be 153.2. Population standard deviation is simply the square root of 153.2, and we just take the square root of 153.2, and we get 12.377. Now, for the sample variance, we have to take this 1,532 And what are we going to divide it by now? What's that? 9. Why 9? 1 less than 10. 10 minus 1. Boom! That will be 170.222, or 0.2 repeating. Sample standard deviation. (13.047). So, give me a moment to catch up on that, because then we're going to see something pretty cool in just a few moments. All right, so what I've done here is I've entered this data into my calculator. I'm now going to do a 1-var stat on this particular list. And look, population standard deviation and sample standard deviation, right there. Can I do that again? Yes. Stat, we go to calc and 1-var stat. Now you will see there's a video on showing you how to do this too. So, and well, it's going to be on this video too. So yeah, I'll always do this again. Thank you for, and that's how it works. 1-var stat. In fact, yeah, does it match? Yeah. So what I want to do is I want to go to the Moodle page and show you exactly where you can find that. Short video on calculator basics. All right, and welcome to the L1. And I'm going to tell for you a little. Oh, that's very basics of it. Histograms and more. Oh, there.
Now the win 0.5.
That's histograms.
Deviations.
Yep, 1-var stats right there. So, yeah, you can add links on Moodle right there. So, I'm going to show you something really cool. Now, the calculator does give you the standard deviations, but what does the calculator not tell you? It doesn't tell you the variance. It does tell you the mean. It would tell you the mean of a set of data. It wouldn't tell you the variance. Now, if you wanted to figure out the variance, one thing you could do is, let me think here for just a second. Yeah, VARs and statistics. If we do SX, now this is the sample standard deviation. It is the square root of the sample, what? Starts with a V. Variance. How would we go in the other direction? If I have the sample standard deviation, I can square that and get my variance. It's under VARs and statistics. So if I wanted to find the population variance, there it is. Pretty cool. All right. So we can also use technology to find the standard deviations and variances of data. In fact, we are going to be using technology. Now, so here's a sample of office rental rates per square footage in Miami Central, bless you, business district. So StatCrunch can be used. Now, StatCrunch is free. Well, you will be using StatCrunch for your first case study. Now, Minitab was something I used back when I was an undergrad. You know, we got it, we had to pay like $5, but we got like lifetime software when I was an undergrad student. TI 8384. You can also do it with Excel, but StatCrunch is what we're going to be mainly using aside from the calculator. When I was in grad school, we used SPSS, which was pretty cool too. All right, so what is the point of standard deviation? We can interpret the standard deviation. It is a measure of the typical amount an entry is going to deviate from the mean. So what happens here is the more the entries are spread out, the greater the standard deviation is going to be. So all three of these data sets have the same mean. But one of these has a this has a standard deviation of none. This data is a little bit more spread out, but this data is most spread. Now, you're going to encounter a question like this on your test. In fact, I'll show you. It's not going to be this exact question, but like you would determine which has there are three options here. Determine which has the greatest and smallest standard deviation. But see, I don't give you any calculations. Obviously, this has the least because not as much spread. This is going to be the greatest because it'll have the most spread. There'll be one of those questions on your test. So, any questions about that? All right, so Chebyshev's theorem, I'm not going to actually put this on the test because I have honestly found that Chebyshev's theorem, it doesn't work for a lot of ways, and we're going to see why. Basically, the portion of any data set lying within k standard deviations of the mean is at least 1 minus 1 over k squared. So if k is equal to 2, what that means is at least 1 minus 1 over 2 squared, 3/4, or 75% of the data lie within 2 standard deviations of the mean. For 3 standard deviations, it would be 88.9%. So the age distribution for Florida is shown in this histogram. If we applied Chebyshev's theorem to the data using k equals 2, what could we conclude? Well, k equals 2, that's 75%. So basically, we would need to go 2 standard deviations above and 2 below the mean. If we went 2 standard deviations below the mean, we get negative. Now, we would have to use 0 since age cannot be negative. Now, if we went 2 standard deviations above the mean, that would be 88.8. At least 75% of the population of Florida is between 0 and 88.8 years old. Now, well, that is true. At least 75%. What percent do you think that would be? Well, Florida is, they jokingly call it God's waiting room. See, when I get old, I'm not going to go to Florida. I don't want to run out the clock there. I plan on running out the clock the same way I'm living now. Doing this. I mean, yeah, they'll take me out. They'll probably have to take me out in a bag or something, but pick me out in a box. Box me up. Did you hear about what happened in Detroit at that funeral home, by the way? Some lady was in a bag. They brought her in, and it turned out she wasn't dead. Yeah, she was breathing. She was alive. They took her to the funeral home. No, I guess the funeral home was supposed to prep her or whatever, but some hospital declared her dead. I have no idea. I mean, we'll never know. We will never know. I mean, what could happen? I mean, my body. Now, what was interesting is one of my coworkers had told me they had to, when she was coming in, she had to be stopped because she was registering a body temperature of 105 because she had her windows down. Now, I have when I come in the morning, I have my AC on, so they asked me, shut off your AC. Yeah, but my window also doesn't work, so they're kind of, some of them have gotten to realize, yeah, my window doesn't work. I really should fix it. But, yeah. So, if we go mean, well, obviously mean minus 3 standard deviations, that's 39.2 minus 3 times 24.8. It is going to be a negative number. Negative 35.2, but we'll just have to say 0. The mean plus 3 standard deviations would be 39.2 plus 3 times 24.8. $113.6. So basically, at least 88.9% are between 0 and 113.6 years old. I'd say that's more like almost 100%. It's probably somebody that's still old enough to remember the day the Titanic sank. I'm going to talk about the coefficient of variation for a data set. Now, what this does, a data set is always going to could have a high or low level of variance, especially when we're comparing two different things, such as heights and weights, or even like grades between classes. This describes simply the standard deviation of a set as a percentage of the mean. So we can find the coefficient of variation for a population and for a sample. The way it will work is it will be either one. You will be told population or sample. So this table here shows the population heights in inches and the weights in pounds of the members of a basketball team. We're going to find the coefficient of variation for the heights and for the weights. So for the heights, and by the way, we're going to use population. So we have to find the means and the standard deviations. And trust me, you are going to be told, use your calculators. You'll be told to use your calculator. So the mean height is 72.8 inches with a standard deviation of 3.3. You take that 3.3 and divide it by 72.8, and you get 4.5% variation in height. So the mean weight is equal to 187.8 pounds with a standard deviation of 17.7 pounds. So the coefficient of variations for the weights is 17.7 over 187.8 times 100%, and that would be 9.4%. Now, when you take your test or have this on a problem set, I'm going to ask you to summarize it in one or two sentences. Basically, I would, all you could say is there is more variation in the weights of basketball players as opposed to their heights. Boom, that's it. Or you could say there's less variation in their heights as opposed to their weights. So we're going to try this example here. Here are the heights and weights of 25 offensive linemen. So we're going to find the coefficient of variation here. Now, obviously, we're going to be using the calculator to figure some of this stuff out. So, and notice, am I wanting to use sample or population? We're going to use sample. So we'll round everything to 2 decimal places. So your job is to figure out these statistics. And then what you're going to do is use that to calculate. So now we're going to do one of our stats on each of these. On L1, and we get a mean of 74.32 for the heights. We'll get a standard deviation of 2.84. Now, let's do the same thing for the weights. So we're going to do a 1-bar stat, but instead of list 1, I'm going to put in list 2, L2. And we get 323.32 pounds for the mean, and for the standard deviation, we get 28.23. Now, the great equalizer, the coefficient of variation for heights, 2.84 over 74.32 times 100%, you get 3.82%. And for the weights, we get 28.23 over 323.32 times 100%. And for that, we get 8.73%. So yeah, trust me, you are going to want to use the calculator to figure this stuff out. You definitely don't want to do that business by hand. But a one-sentence summary would simply be, there is more variation in the weights of football players as opposed to their heights. So that is how we do the coefficient of variation. Now, what I'm actually going to do here, all right, so we're going to do this for heights. And weights. Now, are we using the sample or the population? We're still using sample. So let's go one bar stat. I have L2 there. That's for my weights. My mean is 204.2. Standard deviation is 22.95. Now I'm going to do the one bar stat for list one, the heights. So second L1, we get a standard deviation of 5.54 and a mean of 78.45. So now that is going to enable us to figure out our coefficients of variation. For the weights, we do 22.95 over 204.2 times 100%. 11.24%. Now, we'll do the same thing for the heights. 5.54 over 78.45 times 100%. We get 7.06%. So what can I write as a sentence to discuss it? Just a one sentence. What could I do? What can I say? Yeah, the weights of basketball players. Weights have more variation than heights. That's all I need. All right, so that's going to do that for this particular example. We will see one like this on a test. All right, so we're going to learn how to find quartiles and interquartile range. And also, we're going to learn how to determine whether data in a set of data may be an outlier. So fractiles are numbers that partition or divide an ordered data set into equal parts. The quartiles, basically, they'll divide it into 4 equal parts. You have your first quartile, second quartile, also known as the median, and your third quartile. So the number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed right here. We're going to find the first, second, and third quartiles. So we're also going to do this on the calculator. It's going to be very easy to do on the calculator. So first thing you got to do is you've got to order that data. That's a clear given. You have to order the data. Second thing, so we want to find the median first. Now, what we could do here is we could actually verify this on the calculator. So you know what? Why the heck not? Let's do this on the calculator. So what we'll go ahead and do is we'll go ahead and enter this data on the calculator, and we'll take it from there. Now, we don't have to put it in order, but to do that, we'll go to Edit, and in L1, if you have something there, you want to hit Clear. So yeah, 7, 18, 11, 6, 59, 17, 18, 54, 104, 20, 31, 8, 10, 15, and 19. Now, in order to find all that stuff, let's quit out of here and go to Stat and choose 1 var stat for list 1. And then we calculate and we scroll down. Now, what I'm going to do here is, I'm going to copy this calculator screen over. So what happens is, this shows you how to do it by hand. We learned that the median is 18. Well, the calculator also says that. Now, if we divide each half, we find the medians of each half. There's your first and third quartiles, and as you can see, they're right there. Never will I ever tell you to find a quartile by hand, because in the real world, we just use a calculator. But basically, it's just like finding the median of a lower and an upper set of data. So our first quartile is 10, and our third quartile is 31. So now what we can do with that is use that data to find the interquartile range, or the IQR. All you have to do for that is simply take Q3 minus Q1. And that would be 31 minus 10, or 21. Now, that's going to help us determine any guidelines for outliers, should they exist. So, now that we have our quartiles, and we already know our minimum and maximum values, we now have the 5-number summary. And that's how we're going to make a box and whisker plot. So, how to make a box plot? Real simple. You find the 5-number summary of a data set. So you're going to construct preferably a horizontal one, but you can do these vertically. Scale of values that include the minimum and maximum data values, which are the range. And make sure that they are plotted appropriately. Your 5-number summary, don't just put them equidistant from each other and say, okay, this is it. No. Basically, the box goes from Q1 to Q3, and the median will have another line. And then you draw lines to the whiskers. And there's your box and whisker plot. Now, this is not exactly symmetric. This is what most box and whisker plots should look something not perfectly symmetric. So for our example pertaining to the number of nuclear power plants, we make a box and whisker plot using our quartiles. See, this is what I mean by having it scaled. Yes, that 104 looks to be an outlier. Anyone want to guess what country that's from? Right here. So, about half of the scores are between 10 and 31. Now, if you notice, there are 1, 2, 3, and 4 sections. Each section of a box and whisker plot comprises what percentage of the data? %. Even though they are definitely different size, 25% of our data would be between 6 and 10, 25% here, 25 here, and 25% here. That outlier really throws things off, but that's okay. About half of the scores are between 10 and 31. And that's why we call these quartiles, folks. So for a value to be considered an outlier, we need to calculate two cutoff boundaries, which we'll call the lower and the upper cutoffs. So to find the lower cutoff, you take Q1 minus 1.5 times the IQR. Anything below that is an outlier. For the upper cutoff, you would do Q3 plus 1.5 times the IQR. Anything above that is an outlier. Now, why would we multiply the IQR by 1.5? Well, the statistician, John Tukey, that's Tukey, not Turkey, basically said, okay, 1's not enough, and 2 is too much. True story. And he did that in the 60s. So, that's relatively new in our world of math, when you think about it. So, let's find the cutoffs. The lower cutoff is 10 minus 1.5 times 21, or negative 21.5. There's no values below that, no outliers on the low end. However, for the upper cutoff, we see that we have 31 plus 1.5 times 21, which is 62.5. We do have one value above that, 104, and that's considered to be an outlier. So then we make a modified box and whisker plot. Real easy. The whiskers will just end at the last non-outlying values. Now, in other words, here's what happens. They will not end at the cutoff point. So, for some reason, this did not copy over. But what happened was, that outlier of, 104 gets its own value. Now, this will end at 59. The reason this ends at 59 is because that is the largest value that is not an outlier. Again, you do not put the cutoff of 62.5 there. You do not. All right, so these are instructions, general instructions on how to do that. Now, what I want you to do is we're going to do this one. So what I want you to do, all right, so the first thing we need to do before we can actually find the IQR is the 5-number summary. So the minimum is going to be 12. The first quartile you would get 66.5. The median was 75. The third quartile was 90, and the max was 158. So we find the IQR by taking 90 minus 66.5, and we get 23.5. So if you answered 23.5, you will get a clicker point. If you didn't, well, there are plenty of opportunities throughout this semester. I think last semester, even though we were actually abbreviated, I think I gave away, I think someone got up to like 110 points. So now we want to determine whether we have any outliers. Well, we'll have the lower cutoff, and I recommend putting this on your little formula sheet. It would be 66.5 minus 1.5 times 23.5. So we go to figure out the lower cutoff, and we get 31.25. So do we have any numbers that are below that? $12 and 31. Guess what? It's below the cutoff, it counts. If it's below the cutoff, it counts. It doesn't matter if it was close. Close only counts in horseshoes and hand grenades. So we get low outliers here. Now, let's see if we have any high outliers. 90 plus 1.5 times 23.5. We get 125.25. Do we have any values above that? Yes, which ones? 158 is our only high outlier. So now we're going to make a box and whisker plot. So just going to draw a line here. So we'll take it from 0 to 160. And I'm not going to go in there with a microscope and see just how, if they're close or far off, So here's 80. And we'll do 40 and then 120. So we do have 3 outliers to put in. 12, which is probably about here, and 31. And 158. Now, our median is 75. Our first quartile is 66.5. And our third quartile is 90. So there's our box. Now, where will the lower whisker end? Where would the bottom whisker end at? The 1231 are outliers. It would be 56. And I'm going to mark that as such. Now, where would the upper whisker end? 123. Outstanding. And here you have it, boys and girls. You have made your first box and whisker plot. Pretty awesome, huh? All right. So a one variable stat. So for the IQR, we get 145.5 minus 80 for an IQR of 65.5. Now, what I want you to do is I want you to calculate the lower cutoff and the upper cutoff, and the upper cutoff will go in the clicker in one moment. Let me just set up. There we go. Clickers are open. And don't round it, just give the whole number. So for the lower cutoff, we would get 80 minus 1.5 times 65.5. And yeah, that's a negative number. That's okay. Negative 18.25. Are there any values below that? Any values below negative 18.25? No. So, no low outliers. Now, the upper cutoff would be 145.5 plus 1.5 times 65.5. And for that, we would get 243.75. Are there any values above that? No. So we have a rare case where we have no high outliers either. So in other words, we have no outliers, period. So given our minimum is 47 and our max is 193, here's the thing. We can just do the box and whisker plot straight up. If we go from 0 to 200, so 100 is in the middle. The minimum was 47. The first quartile was 80. Median was 112.5. The third quartile, 145.5. So there's your box. There's your whisker. And there's your other whisker. So that's where it all ends. Pretty good, huh? Now, I'm going to show you how to do this on the graphing calculator. Now, there are instructions on how to do this plot somewhere in the notes. But given that this is a video being made, you'll be able to replay this. So I've entered this data into L1. So first thing I'm going to do is I'm going to go to y equals, make sure I have nothing there. And I don't. So then I'm going to go to second and stat plot. And first thing I'm going to do is I'm going to turn it on. And I'm going to pick the type. Now, these are scatter plots. We're not going to see those until the tail end of the course. The third one is the histogram. We've done that. Now, the fourth and fifth one are box plots. This one with outliers, this one without the outliers. If we choose to do this one, now, when we hit graph, we don't see anything. And so you're probably thinking, I did something wrong. No, you didn't. Go to zoom and hit 9. Zoom 9. Zoom what? 9. Now you can hit trace and you can plot between the values there. So the greatest of these is going to be A. Now that's because even though spread is similar to B and C, what happens is we're getting a larger amount of numbers further away from the mean. And that's why A is going to be the greatest. Now, so the one with the least standard deviation would have the least amount of spread, and that would be C. Now, you could actually have argued, you know what, I made B and C look too much alike, so you know what? Did everyone answer? Yes, everyone answered. Everyone's going to get 2 on this. So, good work. But the answer I was looking for was C. But, yeah, so when you take your test on this, one of these is going to be left blank. So that's how that'll work.